morning, dear students. Today we will spend this session on trying to understand the meaning of atom. In the last class, if I do a quick revision of that, we did talk about the history related with atom. So there were some great philosophers who had somehow concluded that all the matters are made up of small indivisible particles called atomos, right? This atomos is what we used to nowadays refer as atom, which is totally indivisible. And on the basis of that, there were some theories related with that, which we used to call as the law of chemical combination, which constitute two kind of laws. One is the law of conservation of mass by Antoine Lavoisier, who concluded that the mass is constant, that is not changing, whether it cannot be created as well as it cannot be destroyed. Secondly, there was another guy in the 17th century. His name is Joseph L. Proust. His law is also referred to as the law of constant proportion or definite proportion, which says that all the chemical substance, okay, they have all the elements present in them in a fixed proportion by mass. So now we were talking about the Dalton atomic theory regarding the atoms and everything, but we are yet to understand what actually is atom. So today we shall spend this session in trying to understand what is atom. So let us imagine first atom. There is a house. Okay, this house is made up of bricks, and these bricks are further made up of, let's say, maybe clay or cement or many other things, right? And let's say there is another example I'm going to give, ant hill, the place where ant used to stay, right? Ant hill. And in this particular ants, they are made up of grain of sand. These grain of sands are further made up of smaller particles like silica and all of this, right? Okay. So now, if you were asked that what is the building block of this house, you are never going to say that clay and cement, they all are the building block of the house. Instead, you are going to say that the bricks are the building blocks of the house. And if you talk in terms of anthill here, anthill, we never used to say that silica and all the other elements or minerals which are present in the sand, but instead we say grain of sand as the building block of the anthill. So in that way, all the matter which we see, we normally classify the matter into three parts here, that is solid, liquid and gas. And all the matters which we see, they are made up of atom. So atom, as concluded in the Dalton atomic theory, that atom is such a small particle which is totally indivisible, and they are referred to as the building block of almost all the objects which we see in our eyes. For example, let us talk about chair, right? Then we talk about ball. Then we talk about foods. There are many kind of things here, but there is another one, that is living organism. Living organism. So all of these are matter, but in the case of living organism, we have different kind of types here. For example, some living organisms which are mobile, some living organisms come in the form of human, and some in the form of dog. There are different kind of things here, and we knew that this, in the case of living organism, the building block or the structural and functional unit is what we used to call as cell, right? Now this cell is further made up of atom here. Understand? This cell is further made up of atom. So when you try to compare atom and cell, atom is much more smaller, and many atoms combine together to form cell. But you must be thinking, okay, there are many living organisms, right? For example, we cannot say that human being and cow are same. They are totally different. Human being and plants, they are totally different. So this somehow concludes that there are the atom. When we talk about atom here, there are atoms which are different. There are different kind of atoms, right? These come in the form of kinds, different kinds of atom, size, shape, and mass. Understand? So, due to that, different kinds, size, shape, mass, the living organism and all the matters, they come in the form of different kind of forms. Do you understand about this particular thing here? So, now, I will wipe this out first. Let us try to imagine aluminium foil. Aluminium foil. Aluminium foil. I guess aluminium foil are those foils. Many of people, they used to say a silver foil. We used to see the wrapping of the chocolates and everything. We see this kind of foil here. Now, if we have an aluminium foil here, let's say this is the aluminium foil. If we try to maximize it, make it bigger, what we will see is that we will see many different kinds of if we try to maximize this, we will see aluminium here, aluminium. All of these are aluminium, 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 aluminium. Okay. Now, if we maximize this, we will get this. If we are further going to cut this into two pieces here, if we are going to further cut this into two pieces here, I'm going to cut from this part here, okay? What I will get is, I will again get something like this here. This I will get something like, let's say 1, 2, 1, 2, 3, 1, 2, 3, 4. I'll get something like this if I cut this into two pieces here. Now, if this we will cut down into further smaller pieces, we will get something like this here, 2 or maybe 3. That is aluminium here, aluminium here. And all of these are aluminium here. All of these are aluminium. Now, if we cut this into two, again smaller pieces, we will get a singular one. Now, this is what we call as atom. And this particular thing combined together is what we call as element here. This is element here. And this is what we call as atom. Understand? So element generally, element is what we used to say as pure substance. They are pure element, as we used to say, they are pure substance because they have only similar kind of like one kind of atoms here, right? And they have one kinds. Now, as in the case of atom here, atom. What is atom? They are the building block of the matter. Building block of matter. Okay? And secondly, in the case of atom, what we can conclude over here is that in the case of atom, this particular atom here, that is the aluminium atom over here, it should be having the similar kind of properties to that of the aluminium element over here. Is that clear? Whether this particular element, this let's say this aluminium element is really light by nature. So you can somehow conclude here that aluminium atoms are also very light by nature. Understand? So they have similar kind of properties. Similar kind of properties. Is that clear? Now, till date, we have like how many elements present in the world? That is 118. That is 118 elements in the world. Now, Scientists have been trying so hard to name these elements, right? They are trying to name all the elements, and in order to, it will be very difficult for us to remember all the 100 elements in a row. Like you all have a difficult time memorizing all the 36 elements, and maybe 100 element is quite difficult for us to remember. So in order to discuss about the naming of the elements here, I have written over here that is, previously there are like some scientists who adopted a different kind of ways by which they could name the elements. For example, they have named the elements on the basis of the place from where this element was discovered. For example, in the case of californium, these particular elements were discovered in California. That is why his name is californium. And polonium, that is the radioactive element here. And this polonium was discovered in Poland. And europium was discovered in Europe. Understand? So they adopted different kind of strategies by which they could name the element. And in other ways, what they also tried was, they also tried to name the elements to give a tribute to the great scientists. For example, the borium was in tribute to the great scientist called Niels Bohr, whereas rutherfordium is for Rutherford, and Einsteinium is for Einstein, right? So different methods were adopted by the scientists to name the elements. So let's say now they also tried in the case of gold as a yellow. If you refer to gold, normally yellow, the symbol resembles kind of like a yellow, and golds, they are normally yellow by nature, so that is why gold. Understand? So it was the first person who tried to talk about the symbols, the symbol by which we could remember the elements. It was John Dalton. Okay, it was John Dalton. So what he tried to do was, he tried to give symbol to the elements. For example, but according to his viewpoint, he somehow imagined that all the atoms, they are somehow round by nature, that is round or spherical by nature. Round by nature. So on the basis of that, what he did was, he gave some kind of symbols, like for hydrogen, what he did was like this here, hydrogen, okay, and for the carbon, shaded this part, carbon, and for oxygen, he did something like this here, okay, and for phosphorus, he did something like this, and for zinc, he did something like this over here. So now there are like many kind of symbols like this here. You can see in your NCERT textbook here. But it will be very complicating for all of us to remember these kind of symbols to all the 118 elements, if this symbol we are using now. So now the scientists, they were trying to adopt some other means by which they could have a more better or more convenient way to give the symbol of the elements. So let us try to go for it. So this was not convenient here. So what the scientists, they tried to do was, first, the first letter, there are 4 ways. First letter. The scientists, they adopted 4 different methods by which they could name the elements here. The first letter, in that first letter, what this rule was all about is that, for example, hydrogen, carbon, and third was oxygen. What they did was, in order to write the symbol for this, they are always going to use the first letter of the word, that is hydrogen. In the case of hydrogen, the first letter was H. That is why we are going to use H. And the second one, in the case of carbon, is C. In the case of oxygen is O. So this method was adopted first. Now, if we use this particular kind of like rules for naming the elements, then there is another problem here. The problem is there are 180 elements, okay? But we have like 26 alphabets. That is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. That means we have like 26 alphabets. So now for naming 118 elements, we have to repeat again and again. There will be a problem of repetition. So the second rule was the first two letters. So what is this first two letter is all about is, for example, in the case of helium, okay, if we go for the first rule here, that is helium, if we write H, then this is the repetition of hydrogen, same like this, because hydrogen H we are using the first. So this rule is not working. So what they did, the first two letter, that is He, okay, and similarly in the case of lithium, that is Li. Understand? So there are many other things like argon here, that is Ar. Okay, fine. So now here, even if we use this particular concept over here, there is another chances of repetition here. So they adopted the third one, that is the first and third letter. First and third letter. Okay. For example, in the case of magnesium, we go for Mg, that is first and third letter. Okay. In the case of let's say zinc, we go for Zn and Zn N. So there are many other examples. All these kind of like first letter, first two letter, and first and third letter, these are being used in the periodic table in naming the symbol. Now they took the third measure, that is there are some elements which are discovered from different kind of places here, and they have different kind of names there. For example, some elements they were discovered in Latin period and all, and let's say Latin period, and they have a Latin kind of name. For example, maybe Latin or maybe Greek or different kind of places there, right? So let's say sodium here. Sodium, the name of the sodium in Latin word is also referred to as natrium, which is why its symbol is Na. Okay? So in the case of potassium here, potassium, the Latin name of potassium is kalium, which is why we are using K. Understand? The name of iron is ferrum in Latin, ferrum, which is why we are using Fe. So these are the methods the scientists adopted to name, to give a particular kind of symbols to the elements for us to have the better understanding of the elements. Understand? In the previous class, we did talk about the atom and how the symbols were being provided for the atom. Now, in this session, we are going to talk about the relative atomic mass. So, in the sense, normally relative means in comparison with something else. This is what we call as relative atomic, relative, okay. Now, looking at this particular topic here, relative atomic mass, what we are trying to find out that previously when the scientists, they were trying to have some knowledge about the atom, they also wanted to know what are the masses of the atom. So let us talk about this particular topic here, that is relative atomic mass. Suppose imagine there is a fruit seller, okay, and this fruit seller has a 1 kg stone, that is 1 kg stone, okay. This is the standard weight, the standard mass, let's say standard mass. That means this is the exact mass. Now for 1 kg, we are trying to get some apples here. Let's say we got how many apples? 1, 2, 6 apples. Okay. Now this 6 apples, how we got 6 apples? We got this 6 apple in comparison with this 1 kg stone here. So which is why I used to call this as relative mass of apple. Okay, and we always measure in the form of kilogram, that is kg. But when we talk about very tiny particles like atom, it is very difficult for us to measure in the form of kilogram. So we have another set of unit which we used to call as A.MU, which is also referred to as atomic mass unit, which we nowadays we used to call as unified mass. Unified mass, or U. Okay, so now we will try to understand. So that period when there is a very limited kind of information about the elements, atoms, and the existence of the atom, the chemical bonding of the atoms. So that moment, it was like John Dalton, like who was trying to understand. Okay, he tried to refer the law of Proust's law, that is law of definite proportion, which says that in a chemical substance, all the elements are present in a fixed proportion by mass. So background, taking the background information as this of law of definite proportion, we understand that relative atomic mass. Here, let's suppose, imagine here, carbon is reacting with oxygen, it gives rise to carbon monoxide. Monoxide means one single oxygen here. Let's suppose, imagine if this is 3 gram of carbon. 3 gram of carbon reacts with 4 gram of carbon. 4 gram of carbon, it gives rise to 7 gram of carbon monoxide. Is that clear? Now, when we try to understand the relative atomic mass, what we need to understand is that, let's suppose, imagine, okay, let's suppose, what they did was, let's suppose, imagine, if carbon is equal to 1, if they took carbon, 1 gram of carbon, for 1 gram of carbon, they took 1 mu, okay, 1 U of unified mass, they took for 1 carbon, okay. Now over here, 3 gram of carbon. 3 gram of carbon will always react with 4 gram of oxygen. Now if there is 1 gram of carbon, then how many oxygen will be there? Oxygen will not be 1 gram because oxygen is more number, that is 4. So what we are going to do is that I will write over here, fine. So let's say if carbon is 1 gram, then oxygen will be 4. This 4 will be divided by 3. Why? Because over here, please don't get confused here. What I'm trying to tell you over here is that there is a 3 carbon, this will always react with 4 gram of oxygen to become 7 gram of carbon monoxide. Now, I'm making a new situation over here. In that new situation, what I'm trying to do is that, let's suppose, imagine if we take 1 gram of carbon, and that is equal to 1 mu. Let's forget about that. If 1 gram of carbon, if we took 1 gram. Now this 1 gram of carbon will react with 1 gram of oxygen. Is it 1 gram? No, because 3 gram, this is 4 gram. This will be more. So we will try to find out. When we try to cancel this, 3 ones are 3, 1.33, let's say mu. So for 1 gram of carbon, we are getting like 1 mu here. For 1 gram of carbon, we are getting 1 mu. For oxygen, we are getting 1.33 mu. Understand? So now this is the relative atomic mass because it is in comparison with that. So now scientists, they did have a problem with that. Why? Because all these values here, that is 1.33, they are not whole number. They are not whole number. Is that clear? Since if we try to have a relative atomic mass in 1.33, 1.56, it will become more complicated things. So what they try to do, that they went for some other elements, and at that time one of the dominant element was oxygen. Now I'm going to write this reaction once again here. Carbon plus oxygen gives rise to carbon monoxide. This is 7 gram, this is 4 gram, this is 3 gram. Okay, fine. So this particular thing didn't work out. Why? Because we are getting values in 1.33. These are not whole number, and if these are not whole number, our values are going to become more complicated things there, right? So what we did was we took the example. Now in this case, what we did, we referred oxygen here. Now what they did, what they said, let's suppose right, for 1 gram of oxygen, 1 gram of oxygen, they refer it as 1 mu. Understand? For 1 gram of oxygen, they refer it as 1 mu. So now I'm going to write on this side here. Okay? Again here, carbon. If this is 1 gram is equal to, let's say, if oxygen is equal to 1 gram is equal to 1 mu, for this oxygen, I'm sorry, this is not 1 mu, this is 16 mu. 16 mu. So 16 unified mass, 16 mu. Okay? So now, if oxygen for 1 gram there's a 16 U, then how much will be the carbon? Now let us try to find out for that. Okay? So for carbon here, what they tried to do was 3/4 into 16. Right? For 4 is 16, we will get value of 12 U. Okay, so for oxygen we are getting 16 U, for carbon we are getting 12 U. Now this is very nice here. Both 16 and 12, they are whole number, and these values are somehow we will be able to understand. But if in the second option here, we took the example of oxygen, and for oxygen we were totally fine with 16 U and 12 U. But again we are facing one problem here. Because at that time of using that particular concept here, what people noticed was this oxygen was not reacting with all the elements discovered at that time. So if this oxygen is not reacting with other elements, then we won't be able to find the relative atomic mass of the other elements also. So there is a problem again in that. So what they did, they took the example of one thing, that is carbon here. Understand? So why they took the example of carbon? Because carbon is present in almost all living organisms there, and carbon is one of the major things. For example, in the case of human being, carbon is in the form of carbohydrates, like what do you call it? Nucleotides also, right? And in the case of like other living organisms like plants and everything, they are in the form of let's say coal, tree, they are made of carbon itself. Okay, fine. So now this relative atomic mass, in the second one, what they did, they took the example of carbon-12 isotope. Carbon-12 isotope. I guess every one of you are not familiar with this isotope here. Isotopes are elements of a carbon, but they have different mass there. Okay, so relative atomic mass, previously they tried to go for, what do you call, when they first went for the other step, they are not getting the values in whole number, and secondly when they went for oxygen, and oxygen they are getting the value in whole number, but oxygen is not reacting with almost all the elements. So relative atomic mass is mass in comparison to carbon-12 isotope is what we used to call as relative atomic mass. Okay, so on that basis there, right, hydrogen is referred to as 1U, right, helium is referred to as 4U, right. Now all these mass are with reference to carbon-12 isotope. For example, in the case of sodium is 23U, and this all masses gradually laid the foundation for another kind of value called mass value or mass number. Understand? So relative atomic mass means it is the mass of the atom in relative or in comparison to the carbon-12 isotope. Understand? So this is the portion of today's topic, that is relative atomic mass. So I will just try to rewind this part here because this is very important here. Relative atomic mass की concept इतना बहुत same है mid zone पे limited information user अन कौन से की खर्च हो रहे हैं ना कौन से की carbon dioxide ने reaction कौन से की fine share try share कचरा ना 1 mu दी कौन से की 1 mu दी u दी value दी किन जोड़ कचरा ना दी u दी खर्च क्यों लगा किलोग्राम ने मतलब क्या है यो मार कचरा ना किलोग्राम ने पे चिमर हुआ u दी किन जोड़ मतलब you can do the value value carbon 1 u and oxygen 1.33 u. That means value the whole number means oxygen 1 u of oxygen 16 u the chashala and value carbon 12 u or do carbon oxygen problem oxygen element element discovered react chigomor chigimedi ta mansula ta samanya bu react chingin samana bu present union the dominant element go to the element kadire carbon 12 element re which is why so carbon 12 atom the position right ta the relative atomic mass things na current discovered chigolana the atomic mass is in the comparison in relative to the carbon 12 isotope the chashani once again the mass relative atomic mass. This is the concept of relative atomic mass. Thank you.